Khair Mubarak Kareeb. Ramazan Mubarak to you as well. Assalamu alaikum. Okay, Assalamu alaikum everyone. Let's start. So today we are starting our next topic, which is numerical solutions, and we will also call this iteration. So basically, numerical solutions is a category of methods in which in our syllabus there's only one of them, and that's iteration. So we also call this topic iteration because that's what we primarily focus on in this particular topic. Now let's start with this. This is one of the easier topics that we have in our syllabus in terms of the concepts that it has. However, you will see that the questions that you get in iteration, they're not that straightforward because a lot of times in fact, mostly they're going to include differentiation, integration, trigonometry. So you'll have to use all of those other concepts in iteration as well. However, as far as the concepts of iteration itself are concerned, they are relatively straightforward. So we should be able to complete all of them in a couple of days. And then we will spend a day on some practice questions as well. All right, now let's start with this then. So what are numerical solutions? So until now in our syllabus and before that in O-levels as well, we have seen a number of different types of equations. So for example, we have seen equations like these. Let's say 2x squared plus 8x minus 7 equals 0. It's a quadratic equation. We know how to solve this. We have seen equations like these, e raised to power something minus, let's say, 5 equals 0. We know how to solve this equation as well. Using logs, we could solve this equation. We could have some equation that has logs in it, that has ln in it already. For example, ln of x plus 1 plus 5x equals 0. You could have something like this. You know how to solve such equations as well. All right. So this might actually be slightly more complicated, but let's say you have just this. You know how to solve this, right? ln of x plus 1 plus 5 equals 0. You know how to solve equations like these as well. For example, if you have sine of x plus 3 cos of x, that equals 0. You know how to solve this equation as well using trigonometry. So there are a number of different types of equations that we have done in our syllabus until now, and we know how to solve all of them. All right. But there are a lot of other equations that exist, which we haven't covered, and they do not have any standard methods for solving as such. For example, for the quadratic equation, we could use quadratic formula or factorization. For this, we could use logs. For this as well, we could use the concepts of logs and indices. For this, we could use some trigonometric identity. We could use tan equals sine over cos here. For all of these different equations, we have some set methods, okay? But what if we had an equation like this, for example, e raised to power 5x plus ln of 2x plus 1. Then on the other side, let's say you have some trigonometric functions, let's say tan x minus secant x. What if you had a function like this? Now, it's a pretty complicated function, right? Because we have combined a number of these different functions here in one single equation. We can't really solve this directly. At least at our level, we don't have a direct method of solving this. In fact, there does not exist a method for solving this algebraically because there are so many different functions involved here. You would not be able to figure out the solution for this algebraically in this case. So what do we do with equations like these? How do we find the values of x that satisfy this equation? That's the problem, okay? So for some equations, we know how to solve them. For some, we don't have a set method. What do we do in such equations? That's what this topic is about. We have this other method, this different type of method, which is called numerical solution, which we will use to solve equations like these. All right. And these numerical methods, the problem with them is that they don't give us exact values. Like for all of these different equations, we could get exact answers, but numerical solutions don't give us exact answers. They give us approximate answers. But if we use them correctly, we can get answers which are pretty accurate, as in maybe to 3 decimal places, to 4 or 5 decimal places. For all practical purposes, they still serve our purpose. All right. So this is another category of methods now that we have for solving equations, and these are called numerical methods. And we could use them for any equation that we do not have to solve algebraically, like we used to solve these equations earlier. If we can't solve it we don't have a method for solving them like this, we could use numerical methods there. All right. Now, there is one particular method that is in our syllabus, which is called iteration, that we will do in detail. There are other methods as well. They're not part of our syllabus. We're not going to focus on them. Apart from iteration, there are a couple of other things that are also part of this topic. We're going to start with one of those things first of all, and that is about proving that the solution of an equation lies between two numbers. So the general idea that we use here for equations like these is that we say we can't solve them algebraically. So one idea we could use is we could say, let's draw a graph of this function, the one that we have on the left side. Let's draw the graph of this function, the one that we have on the right side. And then we could somehow estimate the solution from that graph. All right, that's one idea that we could use. But if you're sketching a graph, the answer might not be very accurate, right? It's just going to give you an estimate. So one idea that we use to figure out whether to basically improve the accuracy of our answer is that we figure out if the root lies between two numbers. So for example, let me have a graph here like this. Let's say we don't know the shape of these graphs, but let's say we have a random graph that looks like this maybe. Okay. Now, this is one possible solution of this, one possible root of this, of the equation of this graph. Okay, the graph that we have here, one possible root that it has is this point here. There are other points as well, of course. We could extend this line and we could get another root here on the left side, and we could get another root here on the right side. Now, let's say graphically, we can see that there's a root that lies somewhere here. Okay. There's a root that lies somewhere around here. Now, we can't figure out the exact value because it's just a sketch, but we could at least figure out from the graph that what is the estimate, what's the estimated value, what's the approximate value of the solution. Let's say approximately this value is somewhere around on the x-axis, let's say it's 2.3. Let's say we're focusing on this solution right now. The point that I have highlighted here, this is the point that we're focusing on. Let's say on the graph, it seems this value is close to 2.3. Okay. Now, how do we prove, how do we figure out that the solution is indeed 2.3, or how can we increase this accuracy? For that, what we do is we use this idea that if there is a root of an equation like this, on one side of this root, the graph is going to be above the x-axis. And on the other side of this root, the graph is going to be below the x-axis. So on one side, the graph is going to have a positive value. And on the other side, the graph is going to have a negative value. So for instance, if we know that the approximate value is 2.3 and we want to improve our accuracy, we could say, let's see what happens, what the value of this function is at 2.3. So for instance, we have some function, we don't know what the function here is, but let's say if we know a value for x, we can actually write down a random function here. So let's say we have something that looks like this, x cubed plus 4x squared minus 2x plus 1. Let's say we had a cubic function like this, and we were looking for the roots of this function. Now, let's say, I've just written this equation randomly, so it might not have a root that is close to 2.3, but just to give you an idea of how this process is going to work, what we do is we say, let's input x equals 2.3 in this function, in this equation, and see what we get from that. Let's say when we input x equals 2.3 into this, we got a value that was y equal to, let's say, 0.1. All right. Now, this is just a random equation that I've written here. It could be something else as well. You can actually write it like this so that you don't get confused here. Let me say this is ax cubed plus bx squared plus cx plus d. We had an equation like this. We knew the values of a, b, and c. If we knew them, let's say when we input x equals 2.3, that gives us y equal to 0.1. What that means is when the value of x is 2.3, the y value would be 0.1. That may be slightly on this side. So that's above the x-axis. That's 0.1 here. Now, let's say if I input x equal to 2.4, let's say that gave me a value of minus 0.2. That means that value is going to be somewhere here, below the x-axis. Now, at one point, at 2.3, I'm getting a value that is a positive value. At 2.4, I'm getting a value that's a negative value. Now, one y is positive, the other y is negative. Between these 2 points, there's going to be some point where the y value is going to be 0. All right, because you have 1 point that's positive, one that's negative. In order to go from that positive point to the negative point, it's necessary that you pass through 0. Okay, actually just erase this for now. Okay, I can't seem to get rid of this. Yeah. So basically, if you input x equals 2.3, that gives you a positive value. If you input x equals 2.4, that gives you a negative value. Now, in order to go from that first point to the second point, it's necessary to pass through 0. So that means there has to be a solution that exists between 2.3 and 2.4. And now what you could do is, to make it more accurate, you might try inputting x equals 2.35 and see what happens at that point. So let's say at x equals 2.3, you end up getting y equals minus 0.08. Now, what does that mean? We had a number line, so if we could represent these numbers on a number line like this, we started from this, that okay, 2.3 is giving us a positive value, 2.4 is giving us a negative value. Okay, so a solution must lie between these two values, but because between those two values, the graph is going to pass through 0. Now, if we check the middle value between these 2 points, that's 2.35. What do we get at that value? At 2.35, we get a value that is negative. So at 2.35 as well, the value is negative. Now that means the solution should actually be between 2.3 and 2.35 now, because the sign is changing here, going from a positive number to a negative number. So 0 must lie between these two values. So the solution should lie between these two values. Okay. Now, to get more accuracy, what you can do now is you can try the middle value of these two numbers, 2.3 and 2.35, and see what happens at that point. So now you could try, for instance, middle value of 2.3 and 2.35. Let's say you try 2.325. Let's say that gives you 0.02. So you tried another value, which was 2.325, and that gave you a positive number. Now, where's the sign changing? The sign is now changing between 2.325 and 2.35. So the solution must lie between these two values. And you can keep repeating this process until you get to a pretty accurate estimate for the solution of this equation, for the root of this equation, for the x-intercept of this equation. All right. So that's the general idea of numerical solutions. This is how they work. We start with an estimate of the answer. So in this case, we started from this estimate. We said, okay, the solution seems to be somewhere around 2.3. We started from that estimate. And then we said, okay, now let's try some values around 2.3. We tried 2.3, that gave us a positive value. We tried 2.4, that gave us a negative value. Now, in order to go from a positive value to a negative value, it's necessary that you pass through 0. So a solution must lie between x equals 2.3 and x equals 2.4. All right. And then you can just, keep trying midpoints of this. For instance, at 2.35, we figured out it's still negative. So a solution must lie between 2.3 and 2.35. Then we try 2.325. That means the solution must lie between these 2 points, and we can keep getting this value more and more accurate using this iterative process. Okay, so that's the general idea of how this process is going to work. Okay, now what exactly are you going to have to do in this case? Let's start with that. So this was just to give you an intuition of how this process works. Now, what exactly would you have to do? Let's start with the first concept that we need to know here. And that is that you would be asked to prove that a solution of an equation lies between 2 points. That's the first thing that you would need to do in this case. Now, let me give you an example for that. So let's say you have an equation like this. You have x cubed minus x minus 3 equals 0. This is an equation. They might ask you to show that a solution of this equation lies between, let's say, 1 and 2 in this case. Okay. show that a solution of this equation lies between 1 and 2. Now you see it's a cubic function, and that's equal to 0. You do not know how to solve a cubic equation, right? There's no direct method that we have for this. At least at this point, we don't know a method for this. We could solve this if we knew one factor already. So if we knew, for instance, some factor, then we could divide by that and find the other factor, like we used to do in polynomials. But if we don't have any factor, then we can't really solve this equation, okay, using an algebraic method. Now, let's say you draw a graph for this. Let's say this is how the graph looks like. And what it turns out is there is a solution that is close to 1 and 2. And now what you can do is you can prove algebraically that there is a solution between these 2 points. Okay, now how would you do that? This is the function that you have on the left side. Let's call this f of x. The function that you have on the left side here, let's call this function f of x. What is this equal to? F of x is x cubed minus x minus 3. This is what this function is. What we do is we once input x equal to 1 in this function and see what value of y we get from that, what value of the function we get from that. So we first input x equals 1. That gives us f of 1. That turns out to be 1 cubed minus 1 minus 3. What value do we get from this? We get minus 3. All right. And then we input the other point that we're given, x equals 2. Let's see what we get from that. F of 2 equals 2 cubed minus 2 minus 3. And that gives us 8 minus 2 minus 3, which is plus 3. Now, one value that we're getting is negative, and the other value that we're getting is positive. Now, think about it. Whatever this graph was, we have one point where x is equal to 1. We have another point where x is equal to 2. When x is equal to 1, the y value is 3. Right? When x is equal to 1, the y value is minus 3. Sorry. When x is equal to 1, the y value is minus 3. And when x is equal to 2, the y value is plus 3. So this graph has to go from this point to this point. Now, no matter what the shape is, it might be a curve like this. It might be a straight line. It can't be a straight line, it's a cubic curve. So it might be a curve like this, or it might be a curve like this. No matter what the shape of the curve is, it is going to pass through the x-axis at some point between these 2 points. Why? Because one value was negative, the other y value was positive. Now, between these two, when you're going from negative to positive or positive to negative, there is going to come 0. And that is where the root of this equation is going to lie. All right. So what we are doing here is we're saying when we input one value of x, we get a positive value. When we get a negative value. When we input the other value of x, we get a positive value. Now, since one is negative and the other is positive, between these 2 points, the graph of this function has to pass through the x-axis. So there must be a solution between these 2 points. Okay, so once we have calculated this, we write down a statement here, and that's necessary to write. There's 1 mark for writing down that statement. You say, since these 2 values of x are giving us different values of y, which have different signs, a root lies between 1 and 2. So this is how you could write it. You could say, since f of 1 and f of 2, they have different signs. They have different signs or opposite signs. A root must lie between x equals 1 and x equals 2. All right, because x equals 1 is giving us the negative value of y, x equals 2 is giving us a positive value of y. Between those 2 points, there must be some point where the y value becomes 0, and that's going to be a solution for this equation. All right. So this is something that we would have to do first of all. This is the first type of question that you get in this, proving that a solution of an equation lies between two values. All right. Now, let me take another example in this. Let's say you have something like this now. Just copy this whole thing and change it slightly. Okay, so now let's say we have an equation like this. X raised to the power minus 5, x raised to the power 5, sorry, minus 5x plus 3 equal to 2. Okay, we have this equation. Now, again, we need to show that the root of this equation lies between 1 and 2. All right, how do we think about this now? Now, remember in the previous example, we had 0 on the right side. We had 0 on the right side. So the other function that we had on the right side was basically y equal to 0. So that's why we were comparing with the x-axis. We were saying, where does this graph on the left-hand side intersects the x-axis? That's what we were looking for earlier. So since we were comparing with the x-axis, we could say if one value is negative and the other is positive, it's necessary for the graph to cut the x-axis between those 2 points. So the different signs thing works if you have 0 on the other side, because if one value is positive and the other is negative, between those 2 points, there has to be 0. Okay, so this argument only works if you have 0 on the other side. Now, in this case, in this example that I wrote here, you do not have 0 on the other side. Okay, in this example, you do not have 0 on the other side. So how do you prove that a solution of this equation lies between 1 and 2? The first thing you have to do in such problems is you have to convert it to a form such that you have 0 on one side and everything else on the other side. That's what you have to start from. Okay. So in this case, it's going to become x raised to the power 5 minus 5x plus 3 minus 2, which becomes plus 1 equal to 0. So it's necessary to write it in this form first of all, such that you have everything except 0 on one side and only 0 on the other side. This is a form that you need to have before you can use this idea. Okay, so let me write that here on the side. F of x equals 0. The first thing that you have to do in such problems is write your function, write your equation in this form. All expression, everything in terms of x and constants, all constants on one side and only 0 on the other side. Okay. Once you've written it in this form, you would say this thing is our f of x. All right. And in this, you're once going to input the first value that's given here, x equals 1. Let's do that. What does that give us? That gives us f of 1, which is 1 raised to the power 5 minus 5 into 1 plus 1. And that is giving me minus 3 here. Then you input x equals 2. That gives you f of 2, which turns out to be 2 raised to the power 5 minus 5 into 2 plus 1. Let's see what this gives us. 32 plus 1, 33 minus 10, which is 23. This is plus 23. So we have one negative value and the other positive value. What do we say? We say f of 1 and f of 2, the two values that we have calculated, they have opposite signs. It's necessary to write down the statement, otherwise you'll lose 1 mark. It's generally a 2-mark question only. You get 1 mark for evaluating these values. The other mark is for the statement. F of 1 and f of 2 have opposite signs. That proves that a solution or a root must lie between those two values of x. All right, because in order to go from -3 to +23, the curve has to pass through 0. And that is when it will become equal to 0 here. All right, so that's the first idea that you have to use here. You have to prove this thing that a solution lies between two values like this. All right, now let me just summarize this here. Right, I'll just copy the statement from somewhere if I can find that here. Here. Yep. So this is the method that you're going to use for this. You can just note down these steps if you want. So this is the first thing that you have to do in this topic, proving that a solution of an equation lies between 2 points A and B. What's the first thing that you have to do? You have to convert the equation to this form. F of x equals 0. This is necessary. You can't prove this without that. You can actually, but that's going to be more complicated and you will most likely lose a mark there if you try to do something some other way. So this is what you should be doing. Convert the equation to a form like this, first of all terms on one side and only 0 on the other side. Once you're done with that, whatever expression that you have on the left side, you put A in that once and you put B in that. If these two values have different signs, that means a solution lies between x equals A and x equals B. Okay, that is how you prove this thing. Now, there is a condition for this when this idea is going to work, and that condition is that f of x, this function that you have here, that must be a continuous function. Okay, now in your syllabus, you will always get a function that looks like this. The condition for this is f of x must be a continuous function around the given root. Now, what that means is sometimes you can have broken graphs, remember? You can have a graph of a reciprocal function, for instance, that looks like this. Let's take a simple example, y equals 1 over x. How does the graph of this function look like? It looks like this. These are two different parts. Okay. Now, if you try, for instance, in this function, some value of x here, let's say that's x equal to 0.1, you'll get a positive value of x, positive value of y from that. And if you try minus 0.1, you'll get a negative value. That will be minus 10 in this case. So at minus 0.1, you're getting a negative value. At plus 0.1, you're getting a positive value. However, there does not exist a solution of this equation between these 2 points. Why? Because the graph is broken. You have 1 point here and another point here. There is no solution between these 2 points because these points are not joined like this. They don't have any connection. You have one part of the graph that's here, the other part is here. So that rule that we were just discussing earlier, that doesn't work. That doesn't apply in this case. Okay. So for this idea that we have used above to work, the function that you have, that must be a continuous function. Okay, that's basically what this statement means. Now, in your syllabus, whenever you get a problem like this, you will always have a continuous function, so you don't really have to worry about it as such. But just remember for later, if you come across this at some point in your university, just remember this rule only works when you have a continuous function. In A levels, you will always be given a function in such cases that is continuous. So you don't really have to worry about that as such. Okay, so that's the first idea that you have. Now, in the next class, we're actually running out of time today, so we'll have to end this early today. Tomorrow, inshallah, we will be learning how to use iterative formula. Okay, how to use an iterative formula and how to derive an iterative formula. Both of these things you have to know. Okay, you should be able to derive an iterative formula from a given equation. That is part of your syllabus. You do get questions in that, and how to use an iterative formula. We'll do the we will be doing these two things tomorrow, inshallah, and along with some practice questions. And then we will also be doing graphs of different types of functions, because that is also part of this topic. You will get you will be getting different functions for which you'll have to sketch graphs and estimate, for example, the number of solutions that exist for those equations. So that's also part of this topic. We will be doing these things in the next couple of days. Inshallah, tomorrow we do iterative formula, using it and deriving it. And the day after tomorrow, we will be doing graphs of different functions. In fact, we'll just be reviewing how to draw graphs. We have done them already in our earlier topic. For example, we'll discuss how to draw trigonometric functions graphs, how to draw graphs of e power x and ln x. We've done all of that before. You'll need to do all of that in this topic. This is where the graphs thing is normally tested. And then we will spend one day on past paper practice. So we should be done with this topic within this week, hopefully. Let me just see. Thursday, Friday, and Saturday. Yeah, so we should be done with the concepts. We will spend Monday then on doing some practice questions, and then we move on to the next topic after that, inshallah. All right, so that's it for today. I'll see you again tomorrow. Allah Hafiz.